nothing we do after today will be on the second midterm. It's coming up pretty quickly. Maybe a week from Tuesday. So, doesn't mean don't pay attention after today, because it won't be on the midterm. I feel like there's something I need to say, but I can't really think of what it is.
So you have any
No. I guess that's the announcement. Right. Today we're going to talk about topic optimization. And delinquent, I don't remember what part of Stewart that is. Stewart mostly is interested in what we can do with calculus, of course, but I thought I would expand the topic a little, first starting frivolously, and then we'll get to math. I know that students are, whether they're conscious of it or not, are always thinking about optimizing free time. Like, how do you optimize free time? You get all your work done. Hopefully, most of you are optimizing how much you learn. That's always a good thing. Less so in college than in high school, but people often want to optimize their GPA, which doesn't really necessarily reflect on how much you learn, right? It can be a secondary thing. Some of you here might be interested in optimizing your future income. And by optimizing, of course, I mean increasing it to its max, not decreasing it to its minimum. But just from the things I mentioned, you see these can be in conflict with each other. You might have to compromise one thing for another, and you have to make decisions. And what do you use to decide to do that? Well, there are some different principles you can use. You could try and maximize your happiness. Right? In other words, I really want as much free time as possible, but would that really, in the long run, make me happy? Because then I fail and have to bum quarters on the street. So, life is not, in math, it's very simple. You define, your equations, your parameters, and you get a number. But in general, maximizing or optimizing is not always straightforward. Sometimes math actually doesn't work the best. Sometimes it's much easier to create a physical model that models the problem you're dealing with. So if you don't know a lot about physics and you want to know how to build a structure that's strong, you can start with a small structure and try different architectures and see what actually holds up the best. So math isn't always the best way to do it. We did something. I guess I'm going to have to try and bring up the computer here. We did something earlier in the class when we were looking at hyperbolic functions. We looked at soap bubbles, and mouse. So I'm not in the habit of doing this very much, but I hope this video that I found on the subject is still there. It's just about 3 minutes. Oh. So, since it came up, and I have to poke around here a bit, what about passwords, right? You know, you used to be able to put like your birthday or your favorite pet, and you can't do that anymore. Why? Because the people who probably have your best interest in mind, they want to optimize security. Right? Okay, but then you can't remember your passwords. Or you have to use some other program, or you have to write it down, or use some complex strategy that doesn't always work. It's not here. Okay, go to plan B. See if this works. Hopefully I won't get the
It's only natural to dwell on what we missed. The accelerations, dinner with friends.
There we go. Okay, just take a look for what it's
Right,
worth.
so here we are at the bubble tank, which is filled with a wonderful bubble mixture and these wireframe shapes. Now normally, when you blow a bubble, the soap film forms the smallest possible surface area to contain the volume inside of it, and so you get a sphere. With these though, we can start to do the same thing, but with some boundaries involved. So if I take this cube, dip it in the bubble mixture, when we pull it out, the soap film will attach to the boundaries here and form the minimum surface area to connect them all together. So the soap film is calculating the minimum surface to join these edges. And if you then start to change it, so let's take out this boundary, it will adjust to the minimum area. Come in and break. And we have all these other shapes. You can try putting in the tetrahedron over here. So if we dip that in the bubble mixture, we will get this minimum surface area. So it's linked all the boundaries together at a single point in the center. In fact, if I remove one of these, we get that minimum surface area there. Actually, if I take that one out, we might even get a nice, there. Is that it's a saddle point of some description? Someone will email me and correct me on that. And at this point, you can go crazy. We've got all different shapes. Each one will give you a different minimum surface arrangement. So that's the minimum surface area for joining those edges. And if we wanted to calculate that, it would take ages and be a very involved calculation. Whereas the soap film just relaxes straight into that minimum solution. Absolutely incredible. And as always, I'm going to break a few of them to get a slightly more exciting surface. There we go. That is my favourite one. An interesting extra thing you can do is if you take the cube frame, put that in, and you start by getting the minimum, there is the minimum surface area for the cube. You can actually make a few changes to the middle by adding in an extra bubble. So I'm going to try and catch a little bubble. Here we go. So now I've got an extra cube. That central bubble, instead of being a sphere, because of these extra bits of soap film, its minimum equilibrium shape is a smaller cube. This particular shape is what a three-dimensional projection of a four-dimensional hypercube would look like. So there, with bubble mixture and wire frames, you can make four-dimensional bubbles, and that's
Okay, I thought this was a good example of a situation where you could use math to calculate those shapes, but it's a lot easier to just play with soap bubbles. So, I want to bring up, just before we get to the serious math stuff, I wanted to bring up a few things. You can impress your friends with this knowledge. So you've probably heard of something called string theory. If you are a physicist, interested in physics, of course you've heard of it. Kind of a messy area of science, of physics, where they're trying to understand fundamental particles. And the big deal is we've got quantum mechanics on one side and general relativity on the other, and they don't really fit together. So people came up with this new theory, which doesn't seem to help at all. You can't do any experiments with it, but it's in the news, so again, you can impress your friends. So what does string theory do? It says that, fundamental particles, instead of being a particle, they're kind of a vibrating string. I mean, you think of it as, going through some kind of vibration. And these strings pass through time. So if this is our time axis, we do a cross section, we see a loop. But if I'm going to use this diagram here, this is time. If you have a loop passing through time, kind of makes a tube. And one of the things particle physics is really interested in is how particles interact. So in string theory, you've got, these loops passing through time. And then you can have an interaction like this where, they combine and produce other particles. This would be like, you're firing a high energy particle at a target, and out comes this spray of particles. Okay, so the point of all this is that it turns out that string theory is based on a fundamental principle that these interactions minimize the four-dimensional surface area of these tubes. I think is just, given how utterly intractable and complex and not understandable string theory is, well, at least, it comes from a basic, simple idea. Now, it's just a theory, right? People use a theory, they come up with consequences, they want to test the consequences, see how they match reality. And string theory it works very well in explaining what we have, although there are other theories that explain what we have just fine. But it doesn't provide anything new, it doesn't really solve anything. So, okay, that was one example. Yes, sir. Here's another example from physics, much simpler. You have a piece of glass, and you shine a light ray on it. You might know that if you shine it at an angle, it bends. This is the phenomenon where if you're looking down at the water and you see a fish and you grab it where the fish is. The fish wasn't there, he was a little off. That's because light bends when it hits this interface here. Well, it turns out there's another way to look at this than, the light is bending. The other way is, that in a vacuum, light travels at a value called, we call it c. It's a big number, like about 3 times 10 to the 10th centimeters per second. It's very fast. But when light goes through a medium like glass, it slows down. Okay, so let's think about a real-world problem that's similar. You're at the beach. Here's the water. And you see someone out there. You're over here. You see someone out here drowning. And you want to get to them as quickly as possible. And you can run much faster along the beach than going through the water. So you know that if you go straight, you're going to hit a lot of water and it's going to slow you down. But if you were to just minimize the amount of water you're going to go through, that's not the optimal path to this drowning person. Turns out that somewhere in between, there's a path where you minimize the time it takes you to get there. And magically, light seems to know this algorithm, because if you know the speed that light goes through the material, you can use that to calculate this, knowing that this will minimize the time to get from point A to point B. So it's just an interesting physics principle that has to do with optimizing. All right. Any questions, or just we're easing into the real, the meat of this section. Okay. Has anyone here, possibly in high school, run into something called linear optimization? Anyone? You have, okay. All right, you can come up and do, no, just kidding. So here's an example of a linear optimization problem. You have some system that's modeled by, some value z is 2x plus 3y. And you want to minimize or maximize this based on some constraints. So for example, we'll say x has to be greater than 0, y has to be greater than or equal to 0. We'll add another constraint, 3x plus 6y has to be greater than or equal to 24. This could be things like we have a factory and we have 2 different materials we have to buy, and this represents some kind of cost function, and this might represent some other other constraints. All right. So we have these constraints, and we want to optimize z. So doing linear optimization, we don't have to actually graph this. We can do this algebraically, but we can map this. All right. So x greater than or equal to 0 is over here. Y greater than or equal to 0 is here. I'm just gonna draw the these are all linear, right? So they're lines. So we get a line like this, and the other constraint, a line like this, and And so we end up with a region here that we want to maximize or minimize this at. So the actual points turn out to be 4, 0, 2, 4, 6, 8, 2, 4, 6, 8, 8, 0. This is 0, 4. And we have a point here which is 2, 3. So fundamental theory of linear optimization says that the maximums for this function are going to occur at these points of intersection. So all we have to do is evaluate this at these points. All right, well, I guess we have a point here. So for 0, 0, our z value is 0. For 0, 4, it's 12. 2, 3, it's 4 plus 9 is 13. And for 8, 0, it's 16. No, that's not the point. This is the point. It's 3, 0. So that's 6. All right, so here we have the minimum, and here's the maximum. And we don't have to do anything else. We can just graph this, find these points, evaluate the function, and we know that our extreme points will be here. So that's an example. That's an example of using math to do an optimization problem. Now, of course, we're interested in more complicated problems. We now have calculus at our disposal, and so we're going to look at how calculus can assist us in this area. There are a lot of different kinds of problems where this will be useful. The key to solving these problems is to focus on getting past the word problem part. Once you have some equation you want to minimize or maximize, we know we have a very standard technique with calculus. Find the derivative, see where it's 0, tell us whether it's a max or min. We need to use maybe the second derivative test or the first derivative test to see if it's a max or a min. All right, so for this first problem, we have a river, and someone wants to put up a fence. And they're going to use the river as, a border, a boundary. They don't need a fence along the river. And they have 2,400 feet of material. And what do we want to optimize? The volume, the area. So you can think of this as, some farmer has some fencing material. He's got some cows he wants to graze, and he wants to give them the most room to graze on. So we have to turn this into some kind of equation. So if the side here is x, and the single side is y, then it's pretty easy to come up with a constraint. 2x plus y has to equal, has to be less than or equal to 2,400. There's no reason to use less. All right, but what we want to do is we want to maximize the area, which is xy. Well, now we have to use a little creativity here. We want to get this down to one variable so that we can use our calculus tools. So here we have 2x equals 2400 minus y, or x equals 1200 minus y over 2, which we can substitute here. Oh, I'm substituting the wrong one, aren't I? This is y times 1200 minus y over 2. Or 1200y minus y squared over 2. That's our area with respect to y. And of course, now we can find the derivative. So the area y is 1200 minus y. We set that equal to 0, and we see we have a maximum or a minimum at y equals 1200. We could apply we could find the second derivative, minus 1. Well, if it's minus, that tells us, because if the second derivative is negative, that tells us what? Tells us the slope is decreasing, which means it's a maximum. So that tells us the dimension of y is 1200, and you can do some easy calculation, x equals 600. It's kind of interesting. I mean, it's, x is exactly half of y. That's not that surprising. This is a typical optimization problem. The setting up is not that difficult. Okay. Oh, and what is the area here? XY is 720 square feet. This next problem is kind of one of my favorite. There's a name for a certain kind of window that's kind of shaped like this. It's a rectangle, but it's got a semicircle on top. And we have material to do the border, which is 16 feet. So all the way around is 16 feet. And we want to maximize the amount of light we get through the window. We want to maximize the area again. So this is kind of like the first problem, except the geometry is more difficult, and that's where we're going to have fun. So we could give the radius of this circle a value r, and the height up to where the circle starts, h. And then we need an expression for the area. So the area is going to be 2RH, that's rectangle, plus 1/2 pi r squared, which is the area of the semicircle. Now, as I said, the circumference here is limited to 16 feet, so we need an expression for that. That's going to be, we're going to have 2h here, and 2r here. And this half the circumference of a circle. So that's just going to be pi r. And we decided all that has to be 16. Right, so now we just have to do some work here. This is 2h plus 2 plus pi r. And we can solve for h, I guess. Divide by 2. And we get h is 8 minus 2 pi r over 2. And then we can substitute that in here. So we get the area now with respect to r is 2r, 8 minus 2 pi r over 2, plus 1/2 pi r squared. Okay.
Professor,
Did I make a mistake already?
good question.
Okay.
For the 2r, isn't that, wouldn't it be 4r? It's on the
R,
on the top. of
Which 2r?
In the circumference. You'd be at
Okay.
the top and the bottom, correct?
Okay, so the circumference is this piece, that's 2r. This and this, that's 2h.
Oh, no, okay, never mind.
Pi times diameter, or just pi r. Okay. Alright, well, now we just have to do some math. So let's simplify this here. This is 16 r minus 2 pi r squared, 1/2 pi r squared, is that right? I feel like I already made a mistake, but let's see, 2h, 2 pi plus r, 16, h is 8 minus. Okay, we plug this in here. All right, looks okay. I guess this is 16r minus 5/2 pi r squared. And so what's dA dr here? 16 minus 5 pi r, which we want to set to 0. So we get 5 pi r equals 16, or r equals, yeah, no, that's the wrong answer. What did I do wrong here? Find out over here.
So for the height, there is an 18 minus 4 pi r.
I appreciate your assistance. Do you think it's something to do, is there a math error you can point me at?
So, for height, so if you go back to these problems to get there, when you divide by 2, that's not what it equals.
Oh! Thank you. Two plus pi right? Okay. Plus pi for 2r. So that becomes 16 plus 16 minus 2 plus pi r, 1/2 pi r squared. Does that sound right? Okay. Oh no, that's r. This is r squared. So we have 16r minus r squared times 2 plus pi over 2. I'm just going to keep going and see if I have my cheat sheet, so if I get too far off, I can catch it. Okay, 16 minus 2r times 2 plus pi over 2. 16 minus 4 plus pi. We set that equal to 0, we get r equals 16 over 4 plus pi. Okay, that's what I was looking for, yes. Thank you for catching me. Okay. How do we know that this is a maximum? Well, we can find the derivative again. That'll be negative 4 plus pi. It's negative, so it's a maximum. And you can complete this. If that's r, then you just have to plug in here, find out what h is. So that's how to maximize this. There's a problem, I think there's a homework problem like this in the book. And apparently this has a name, but I can't remember. Some kind of, named after someone, I guess, created this window. All right, so again, that's what most of the number of these problems are going to be this way. They're going to be geometric. I'm going to do another one. So you have a variety of what you might find. Next problem, got a semicircle. And you want to embed a rectangle in it. Well, you probably see you can embed many rectangles. But what we want to do is embed a rectangle with the maximum area. So how do we go about that? Well, it might help to treat this as a circle on a plane. And our 2 points here are, well, we'll just give them the names x, y. And this point is negative x, y. I guess we have some radius r here. And we know that the area is just going to be equal to x, 2xy. Right? 2 x's and a y. These points have to be on the circle. So we need the equation of the circle is x squared plus y squared equals r squared. So it's a capital R. So we need to solve this for one of these variables. So let's just say y equals plus or minus the square root of r squared minus x squared. Well, I think the minus would be down here, so we can eliminate that. So our area is 2x times the square root of r squared minus x squared. In terms of, whatever x we pick here. We can do kind of a sanity test here. What if x is 0? So I have like a infinitely thin, skinny rectangle. Well, 2 times 0 times r is 0. That's what you'd expect. And what if x is out here? X can't be created in the radius. X is r squared minus r squared is 0, so again you get 0. So it passes the sanity test. Now we just need to find out where this x should be to maximize the area. All right, so the a dx. This is a little bit more of a challenging derivative problem, I guess. So we leave the 2 outside, so that doesn't matter. And then we have to use the product rule. So it's going to be square root of r squared minus x squared times the derivative of x, which is 1, plus x times the derivative of r squared minus x squared. Well, what do we know that to be? It's going to be 1 over square root of r squared minus x squared. So the square root of x is 1 over square root of x. So, over 2 times the square root of x. But the chain rule requires I multiply this by the derivative of r squared minus x squared. All right, so what's that? That's minus 2x. Again, I'm suspicious. Oh. That looks horrendously difficult, because it is. It's got to be a little, you have to have a little bravery in you when you go after these things. So we want this equal to 0. Yeah. Right. Maybe I want to multiply through by 2. Save some trouble. So I have 2 times the square root of r squared minus x squared plus minus 2x squared over the square root of r squared minus x squared. And we want to set that equal to 0. So obviously we want to multiply through by square root of r squared minus x squared. That will be 2 times r squared minus x squared plus maybe 2x squared. Okay, 2r squared is x squared is 2x squared is 0. Or just it's wrong. Going. So x squared equals r squared over 2, or x equals r over the square root of 2. sorry?
Was when you decided to multiply the two out, to both of the.
I apologize, just gonna have to speak.
So when you multiply two out, first row,
Oh, here, I
Yeah.
multiplied,
you multiplied it onto the first one and onto the second one.
there are two terms here, right?
Uh-huh.
So 2 times this and 2 times this,
Oh, just kidding, never mind.
and then I cancel that. I went pretty fast. Okay, got that? So, square root of 2, that kind of sounds like something. This is R, and then this is R over the square root of 2. That means this distance means if you had a box like this, oh, of course, this is R, right? So what you have here is a square and another square. You know, often with these problems, you'll see that kind of symmetry show up. All right, let's take a break for a few minutes, and we'll look at a different kind of optimization problem. I'm not an economist, but sometimes I play one in math class. So we're gonna do like the 60-second version of basic economics. The idea is you have a supply curve. What's a supply curve? Well, it tells you at a certain price, you know, for some commodity, you know. It's a good commodity. Windows, okay. At a certain price, how much are, you know, how many will manufacturers be willing to provide? So the idea is this curve kind of, in a very superficial way, is increasing. The more you can get for your window, the more windows people are willing to build for you. And you have over here on the other side, demand. And again, it's dollars and numbers, except this is given a certain price, how many people are willing to buy it. So figure you have an automobile for $10,000, you get a lot of customers. For $100,000, not so many. So this is kind of a decreasing curve. And the idea is you kind of lay one on top of each other, and at some point they intersect, and that gives you some ideal price to charge for something where the supply will meet the demand and you won't have any over demand or under supply. That's well and good. That's maybe how we call this microeconomics, how the market might work on a particular product. But you, as the window manufacturer, you might have some other ideas. So you're not necessarily interested in making just enough windows to sell them all. You're also interested in profit. The first window you make is more expensive, right? You have to design it. And as you start manufacturing, you order materials to make it, And the more materials you order, you know, the lower the price you can get, because you're involved in the economic market too. So, I guess we could stick with Windows, that works. So we're given that the profit on a single unit for some window is $500 minus 0.1x, where x is the number sold. That is to say, after I sell 100 of them, I make more profit because my costs have gone down. I guess this is just like the startup costs, but then there are the overall costs, which have to do with how many you sell. So we're given that cost for each item is, well, these are actually very fancy windows. These are big stained glass windows. We don't have that many customers for. These are $100,000 plus 100x. In other words, our cost is only going to be $100 once we pay off our startup amount. So our revenue, that's the profit, is going to be the number sold times px, which is going to be x times 500 minus 0.1x, or 500x minus 0.1x squared. That's the revenue we get for each of these.
Where'd you get the 500?
Okay, I actually, I'm not explaining this right. This is the profit we get from each unit based on how many we sold. This is the cost to manufacture them. So the revenue is the profit we get from each. That's just the money that comes in. It's not what we make. It's not the profit. It's just the revenue. This is profit per unit, I guess is the way to put it. So we have the cost, to create these, and the revenue is this product here. Ask questions, because I'm not an economist. Let's get this right. We're manufacturing something. The more we manufacture, the lower, the more we manufacture, regardless of how many we manufacture, there's built-in costs. On each unit, we get a certain profit, and the number of units we sell times that profit is the revenue, the income. So this is our cost, this is our revenue, so this is small p. Our big P profit is what? It's going to be our revenue minus our costs. That's where we're developing this problem from. Okay, so we have a model for the revenue. That's 500x minus 0.1x squared. And we have our costs, so it's minus 100,000 plus 100 x. That's our P profit, overall profit. And what do we want to do? We're manufacturers, we want to maximize our profit. So now we want to figure out how many units do we want to sell. Right? Yeah. There's something fishy here, but I'll figure it out before we're done. Okay, so really, now we've got an economics problem that we've turned into a math problem. And all we have to do is find the derivative and find out where it's 0. All right, so how do we do that? So we've got 500 minus 100 is 400x. We've got minus 100,000 and minus 0.1x squared. So the derivative, well that's P, derivative is 400 minus 0.2x. And we want to know where that's 0. That's x equals 400 over 0.2 or 2,000. So that's how many units we want to make. I guess the question is, how much profit is that? So what is that? 400 times 2,000 minus 100,000 minus 0.1 times 2,000 squared. Is that right? No. No, x. X. I think that's right. Well. What do we get here? 800,000 minus 100,000 minus 400,000. So that's 300,000. We're going to have to sell a lot. We're going to have good salesmen, I guess, sell that many. All right, well again, it's the same idea. You have to construct equations to describe your problem. And from there, you can minimize or maximize using the derivative. All right, one more problem. It's just kind of an abstract one, but a typical math problem. This is a minimization problem. We have a curve. It looks like this. And we want to know, well, we pick a point here, 1/2. On the axis. We want to know what the shortest distance is from this point to our graph. So this point is 1/2, 0. So how do we go about that? Well, any point on this curve is what? It's x x to the 3/2. And we have to use our distance formula, which, you know, is the square root of x1 minus x2 squared plus y1 minus y2 squared. And we want to find x, you know, we want to find the x point, you know, x and y that makes this the minimum. Now, you can save a lot of effort here if you kind of think this through. If I want to minimize d, it's just as well to minimize d squared. If you go through this using d, it would work the same, but you know, a lot more trouble. So let's try and minimize d squared here. So we use the formula, so we could say x minus 1/2 squared plus x to the 3/2 minus 0 squared, or distance squared. And we find the derivative with respect to x as what? Well, okay. This is just x cubed, that's nice. This is 2x minus 1/2 times the derivative using the chain rule, which is just 1, plus 3x squared. And we want to set that equal to 0. All right, so what do we have? 2x minus 1 plus 3x squared equals 0, or 3x squared plus 2x minus 1 equals 0. Looks like a quadratic. I'm just going to apply the quadratic formula. Plus, because it's a minus 12, 24. Where have I seen this before? Wait. 4AC is just 12, isn't it? Over 2a, 6. So it's -2 plus or minus square root of 16 is 4 over 6, or I'm not getting what I would, oh, no, I see. Okay, 1 or 1/3. That's interesting. A solution here -2. Oh, well. So -1. Why do we have a -1? Well, we squared this, right? So we end up, this is we call it like a phantom root. If you plug it in, you get a minimum or a maximum here, but it doesn't really apply to this curve. So this x here is 1/3, 1/3 to the 3/2. Just the point that has a minimum distance. Okay. So you're going to learn more about this just by in the homework. There'll be a variety of problems, and you just have to work through finding the equations and then follow follow the pattern, find the derivative, see where it's 0, see where the min or the max is. Are there any questions about this? Okay. I have another small subject that I would like to squeeze in, but I'm sure it's necessary today. Yeah, I'm going to save this for another day. All right, I guess that's all I have. If you have any questions, you want to stick around, I'm here for a while. If you have a calculator, if you would try and bring it next Tuesday,